Hello all. I'm missing all kinds of stuff this weekend. Oh my God. So I'm going to get you guys started, and then I have to go get another pad of paper. So it looks like my workstation's all out of them. We are done with new material. Our only job for Monday and Wednesday is to review for exam 3. If there are any particular topics that you feel like you could use some more work with, I am happy to write questions on the fly for any of those. I really like our backup chapter problems for chapter 7 and chapter 6 both, but I thought it might do well for us to do a little bit of practice with stoichiometry. Come on, here we go. Let's start with number 50 together. What mass of silver oxide, Ag2O, is required to produce 25 grams of silver sulfadiazine in this reaction? I'll make it a little bigger for y'all. So number 50, give this one a shot. Big molecules, but same principles that we've been using for quite a while. All right, see if you can figure this one out. So this problem's a little bit different. Can anybody sort of talk me through how this problem might be a little different than what we've seen before? What makes this problem odd in terms of a stoichiometry problem compared to the ones that we've seen so far?
Too many maths.
Too many what?
Math.
There are a lot of atoms in it. I suppose that's one thing. But I hope that you guys can add up all those atomic masses to get a molar mass at this point, even though it is kind of a pain in the butt. The weird thing to me about this one is the fact that instead of starting out with an amount of a reactant that we know, we're starting out with an amount of product that we know. So in this case, instead of trying to figure out how much of something we're going to make, we already know how much we want to make of the product, and we're trying to figure out how much of the reactant we need to make it, right? So this one's a little bit backwards, but big principles are always the same in stoichiometry when we're working with balanced chemical equations. If we know a number of moles of something from the balanced chemical equation, we can always use that to find a number of moles of anything else that we want from the balanced chemical equation. So if we can find out how many moles of our silver sulfadiazine, whatever that stuff is, that's actually probably a really cool looking molecule. We won't take a look at it and take too much of our time, but that might be worth a Google search to look at that in a little more detail. If we know how many moles of this we have, we can use the coefficients in the balanced equation to figure out how many moles of our silver oxide we need to put into the reaction, right? Okay. That's not a very effective writing implement. Let's do better. Much better. So if we convert any chemical formula from grams to moles, we're going to use the molar mass, adding up all these atomic masses in this formula of a silver, 10 carbons, 9 hydrogens, 4 nitrogens, a sulfur, and 2 oxygens. Did anybody do this? How many grams are there in 1 mole?
I got 300. Oh.
Well, we heard 300 something twice, which is good.
I got 357.17 grams of silver sulfadiazine.
357.
0.17, yes.
0.17 grams. Okay. And I saw a couple of nodding heads, so that much confirmation's probably okay for us. So we won't even write the entire formula out again. That's silver sulfadiazine. I'm not even going to write out the whole name because even the name is a little bit cumbersome to say. But from our balanced chemical equation, we can tell that for every 1 mole of silver sulfadiazine that we want to make, for every 2 moles of silver sulfadiazine that we want to make, we have to put in 1 mole of silver oxide. Right from those coefficients in the balanced chemical equation. And then finally, since the problem asked us how many grams of silver oxide we had to put in, and right now we know how many moles we have to put in, we have to convert those moles of silver oxide back into grams by using the molar mass of silver oxide. Somebody got our molar mass of silver oxide? It's amazing how fast those masses add up when you put silver atoms in there. They're huge.
I got 231.74 grams.
Awesome. And I didn't do these problems ahead of time because then it's really boring for me. There's nothing worse than a performance that's over rehearsed. And because the only number of significant figures that we have going in is our 3 significant figures in the mass of silver sulfadiazine, assuming that our molar masses all have more than 3 sig figs, which they do, that's going to be the limit for the number of sig figs we can keep is those 3. So rounded to 3 sig figs, it looks like we're going to need 8.11 grams of silver oxide to put into this reaction. If everything goes perfectly, that should be enough to make 25.0 grams of silver sulfadiazine. Now, in real life, would we want to use the bare minimum amount of the reactant if we absolutely needed those 25.0 grams? I mean, it depends on the reaction, I guess. It also depends on how confident you are in your ability to isolate that product. Me, I would probably add an extra 15 or 20% and make sure that I had enough to make my 25.0 grams in case, you know, reactions don't always go perfectly. It's just the way it goes. So if our percent yield was 100%, then that should be enough to make our 25.0 grams of the silver sulfadiazine. Ooh, I really like this one a lot. So we talked about acid-base reactions. This is an acid-base reaction. In order to figure out if we used enough of our neutralizing agent, sodium carbonate, you have to actually write the reaction here. All right, so nitric acid, we spilled 2.5 kilograms of it. That is a metric crap ton of nitric acid. That would be a major, major problem in a laboratory if you spilled that much nitric acid. It's nasty. Love this because we get to do a limiting reactant problem, which is great. And we get practice thinking about how acid-base reactions work and what their products look like. It even gives us a little bit of a clue here as to what's going to happen. We've been graced today with the presence of my shy cat, Mr. Edgar. Mr. Edgar, say hi to the camera. Oh, he doesn't want to be on camera. Oh, okay, okay. You're the one who came in here, buddy. It's like, no pictures, please. So if you're having trouble getting the balanced chemical equation, that's kind of the harder part of this, or the part we've had less practice with anyway. First of all, we have to remember what nitric acid's formula is, which means that's like from last exam, but we really can never forget anything in the world of chemistry. It's all
HNO3.
HNO3, very good. Remember, it's the acid that comes from nitrate, NO3 minus. So because there's a -1, we know we need one H plus to go along with it, which is why there's only one H with NO3. Nitrate, the ate suffix turns into an ic acid when we turn that thing into an acid. So the acid that comes from nitrate is nitric acid. And then sodium carbonate, I just used some of that stuff today to make some dishwashing detergent because I was out and couldn't get away to the store. If you buy this in the grocery store, they call it washing soda. Now, generally speaking, acid-base reactions function as double replacements, all right? So if we had a hydroxide base, like sodium hydroxide, then we would expect water to be one of the products of the reaction because we'd have an H plus ending up with an OH minus. Here, we're putting together H pluses and CO3 2 minuses. All right, now in the long run, that H2CO3 is not going to stick around, but we could write it that way. It wouldn't be a big deal. So if this is a double replacement, we're replacing sodiums with H pluses, so Na pluses with H pluses. And because H plus is a +1 and Na plus is a +1, that means that the correct formula, when we put together our H's and our CO3 2 minuses, has to be H2CO3. So the reason they talk about carbon dioxide being released is because anytime we make this stuff in a chemical reaction, it decomposes pretty much instantly. So I'll show you what happens in just a second. All right. And then we have Na +1s and nitrates that are -1s, which means we only need one of each of those to make our formula NaNO3. Is this a balanced chemical equation? Okay, so I guess we better balance it. It looks like there are 2 sodiums on the left and only 1 on the right. So let's fix that. Now it looks like we've got 2 nitrates on the right and only 1 on the left. We better fix that. And now it looks like we've got 2 H pluses in the 2 HNO3s and 2 H pluses in our 1 carbonic acid. Balanced chemical equation. Now, this is perfectly fine for us to go and solve the rest of the problem with, but if you're wondering where the CO2 comes from, anytime we make H2CO3 in a reaction, and this is something that you guys have, I think, seen before. Anytime you put together sodium bicarbonate and vinegar, right? Baking soda and vinegar, that's what you're making, carbonic acid. Why does it bubble? Because as soon as you make it, it breaks apart into water and CO2. Okay, now, that being said, we have a balanced chemical equation that we can use to do our stoichiometry. After writing that reaction and balancing it, we realize that it takes 2 nitric acids to react with every 1 sodium carbonate. All right, so let's see if we can finish the rest of our problem. And there are multiple ways to approach this, for sure. we could do stoichiometry to answer the question. If I start with 2.5 kilograms of nitric acid, how much sodium carbonate would I need to neutralize all that nitric acid? All right, so we could do the work to answer that question, or we could instead do the stoichiometry to answer the question. If I started with 2 kilograms of sodium carbonate, how many kilograms of nitric acid could I neutralize? Either one of those ways of approaching the problem would be perfectly fine. So I'm going to pick the way that I think the least of you picked. But really, either way of doing this problem is perfectly fine. What I'm going to do is I'm going to start with my 2 kilograms of Na2CO3. All right. So I have 2 kilograms. And I assume that they know we have 2 kilograms to at least a couple or 3 significant figures. All right. They're not very careful when they wrote this problem with significant figures. So let's say 2.00 times 10 to the third grams. So that is 2 kilograms of sodium carbonate. Let's do the stoichiometry to see how many kilograms of nitric acid we could neutralize with this. All right. So how would we do that? Remember, we got to get to a number of moles of sodium carbonate in the balanced chemical equation. And then from that, we can use those coefficients to convert into how many moles of nitric acid we could neutralize. So every 1 mole of Na2CO3 has a mass of how many grams? I'm sure you guys used that at some point.
105.99.
Doesn't sound like enough for some reason. 48, 58, 60, and 46. Yeah, okay, that's perfect.
Okay.
Good job. Sorry I doubted you. The math didn't seem to work in my head for a second. Now, from our balanced chemical equation, we know that for every 1 mole of Na2CO3 that we use, we can neutralize 2 moles of HNO3. And HNO3's molar mass 63 point something. 48, 58, 62.
02.
63.02. So every 1 mole of HNO3 has a mass of 63.02 grams of HNO3. And I'm not even going to bother converting back to kilograms because that's really easy. Hopefully we can all do that pretty simply at this point. So my calculations are saying that my 2 kilograms of sodium carbonate could neutralize 2.38 kilograms of HNO3, which means we didn't use quite enough sodium carbonate, right? So if we had calculated more than 2.50 kilograms here, that means that the math would have worked out that we had had enough of our sodium carbonate to neutralize all the HNO3. So it looks like our math told us we could only neutralize 2.38 kilograms of nitric acid with our sodium carbonate. So not quite enough. Still, we neutralized most of it. All right, we're a lot better off than we were when we had 2.5 kilograms of nitric acid around.
I have a question.
I might have an answer.
Okay, so I understand like the question or the answer makes sense, but so after the 1 mole over 105.99, so you said 2 moles of nitric acid over 1 mole is equal to 1 mole of the Na2CO3, but I see that they're on the same side, and I thought that you would get if it would be equal to if you get it on the other side, if that makes sense.
So what you convert into from the balanced chemical equation is all about what the question is asking about. Here, what we were asked about is, we know how much of this we used, and it's asking, did we use enough to react with all of this stuff, right?
Yeah.
That's what the question was asking about. So it's perfectly valid to convert from a number of moles of one reactant to a number of moles of another reactant if the other reactant is what the question's asking about, right?
Okay.
Does that make sense?
Yeah, it does.
So
Yeah.
that's another reason that I chose this problem, is because we can't just memorize how to do the same thing over and over again when we do stoichiometry. It's very dependent on what the question is asking, right? There's no way to memorize your way through this. So what we do know about this system is that we know that we need 2 moles of, we know that we need 1 mole of sodium carbonate to react with every 2 moles of nitric acid, right? That statement is the statement that allows us to solve this whole big problem.
Okay.
Okay?
Okay. I understand now. Thank
Sweet.
you.
Yeah, absolutely. And that's exactly why I picked this problem. So what I'm trying to do is I'm trying to make us look at as many completely different ways of applying balanced chemical equation stoichiometry as I can, so we get out of just memorizing a way to do grams to moles to moles to grams, reactants to products over and over again, right?
Okay. Yeah.
In the end, stoichiometry is so much more powerful than that. It's a big picture thing. So it's the basic principle that if we know the balanced chemical equation, we know how many moles of each reactant and product are required to make that reaction run the way it's supposed to. And if we can find a number of moles of something based on what our experiment has told us or what the problem is telling us, then we can figure out anything else from that.
Got
Okay?
it. Yeah.
I'm trying to force you into the big picture instead of the little picture. And the big picture is sometimes we do take a number of moles of a reactant and solve for a number of moles of another reactant. That's what the problem had us do this time.
Okay.
Okay. Mia,
Yeah.
your hand's raised. What can I do?
Yeah, can we work on solubility at some point this week as well?
Solubility?
Yeah.
Sure. So remember open book, open note, not open internet searching. Pick the solubility table that you like the best and use that on the exam. All right, so let's look at a couple of problems from the solubility section. There are a lot of really good redox practice problems in this backup chapter assignment as well. Come on. All right, I guess I'm gonna have to write one myself. That's fine. We shouldn't expect other people's assignments to do everything for us. Sometimes we have to take matters into our own hands.
Ooh.
All right. So let's say we are mixing gallium nitrate and ammonium carbonate. Try and write for me the balanced chemical equation for mixing those two things together. All right. And I should be more specific. Solutions of gallium nitrate and ammonium carbonate are mixed. So these are both dissolved in water at the beginning. So you will have your periodic table available to you. Here's gallium, the metal in an ionic compound. What's gallium's charge in an ionic compound?
+3.
Has to be +3. It's a group 3 metal, right? Okay, so if gallium's a +3 and nitrate is NO3 with a -1 charge, then that must mean that when we put those together, the correct formula has to be GaNO3 3. And that's a solution, so we're going to mark it aqueous. We put that together with ammonium carbonate. I was really evil here and just did 2 polyatomic ions mixed together. So you just have to know their charges. Ammonium is NH4 plus, carbonate is CO3 2 minus, which means we need 2 ammoniums for every carbonate in that formula. Sarah, I'm sorry I was so mean. I saw that head shake.
No, I read ammonium as aluminum, and so I put Al, and I was like,
well, aluminum carbonate, here's your context clue that can't be right. Aluminum carbonate is not soluble in water at all. All right.
Yeah, that's what I was like. And then I see that you said, okay.
So what are our possible products here? All right. If we mix these 2 ionic compounds together, the likeliest thing that can happen is a precipitation reaction. All right. That's the kind of thing we're looking for when we mix ionic compounds. Sometimes other things happen, but if this is a precipitation reaction, we would have to determine whether gallium carbonate is soluble or insoluble, and also whether ammonium nitrate is soluble or insoluble. So first of all, what's the correct formula for gallium carbonate? If our galliums are +3s and our carbonates are -2s, then our correct formula for gallium carbonate would have to be Ga2CO3 3. And if ammoniums are +1s and nitrates are -1s, we only need 1 of each of them. So we also have to figure out whether or not each of these things is soluble. All right. If you use the tables in your book, which fine, all right, it's pretty easy to do that, and it covers a ton of stuff, but not everything. Here's our solubility table in the textbook. It looks like if our compound contains ammonium ions, and BTW, this is a little bit under, I think they should have included a couple more ions in here. Ammonium or nitrate ions will make something soluble. All right, so there aren't any exceptions to that, which means we can assume that our ammonium nitrate is still dissolved. It's aqueous. So now let's look for gallium or carbonate anywhere in these tables. All right, I'm not seeing gallium or carbonate any place in the soluble ions list. Oh, right here, it says these ions make an ionic compound soluble with no exceptions. Nitrate's in there too. So since ammonium and nitrate both make something soluble, I call that kind of compound double supersoluble. All right, which means ammonium nitrate, you could dissolve a metric crap ton of that stuff in water. Insoluble ionic compounds. Oh, look, carbonate right there. So it looks like carbonates are going to be insoluble. In other words, they're going to make precipitate unless they're with a group 1 cation or ammonium. Okay, so since carbonates are generally insoluble and since gallium carbonate isn't one of those exceptions, we would anticipate that gallium carbonate would form a solid, would make a precipitate. We're not quite finished yet because this is a reaction, but it's not a balanced reaction. All right. It looks like we have 3 nitrates on the left, only 1 on the right. It looks like we've got 2 ammoniums on the left and only 1 on the right. All right. So how do we fix that? with, it looks like we have 2 galliums on the left, only 1 on the right. Let's fix our galliums first. All right, so if we do that, that means now we have 6 nitrates on the left and only 1 on the right. We can fix that problem. Now we've got 6 ammoniums on the right and only 2 on the left. Let's fix that problem. And now we've got a balanced chemical equation. Mia, was that a helpful example for us looking through the tables?
Yes, I was very stressed using all of the YouTube sources yesterday, finishing my homework.
So my advice to you is pick a solubility table that you like and can read quickly and use it. All right, you get to pick your resource for this. The one in the book is fine. I'm not going to give you something exotic enough that you can't use the book resource to figure it out. All right, I'm not that mean, promise.
If you're not mean, then why didn't you tell me that I totally forgot to upload problems to my exam, and then let me just go missing those problems?
What are you talking about? Where? When?
Exam 2, I totally forgot to upload a whole page.
Well, I mean, by the time I get around to grading them, it's probably like a little bit too late to fix. Did you have the test page? You just didn't upload it?
No, it's my fault. Yeah, I have the page. It's in my notebook. I just forgot to upload it.
Mia, why didn't you?
I know.
Why didn't you email me right away? All right. Ah! Okay, so what I want you guys to do now is, since we are reviewing for the exam, why don't you take this molecular equation and write total and net ionic equations for it, all right? So now that we wrote the balanced chemical equation, give me the total and net ionic versions of this equation. So remember, in our total ionic equation, the principle here is that soluble ionic compounds dissociate in water. They break apart into their individual ions in water. So what ions are there in those 2 gallium nitrates? I see 2 gallium 3+ ions dissolved in water, and I see 2 times 3, so 6 nitrates dissolved in water. Really important here, it is an ionic equation. Don't forget to write the charges of your ions, all right? In those 3 ammonium carbonates, I see a total of 6 ammonium ions dissolved in water and a total of 3 carbonates with -2 charges dissolved in water. I could never write a total ionic equation on one line. I just don't have enough space. So let's write our products now. The first product, gallium carbonate, isn't dissolved in water anymore. So because of that, we are not breaking it apart into its ions. It is not dissociated any longer. However, ammonium nitrate, those 6 ammonium nitrates are still aqueous, which means that at the end of the reaction, we still have 6 ammonium ions dissolved in water and 6 nitrates dissolved in water. So that is our total ionic equation. It shows all the ions present on both sides. We can write a simpler version of this equation called the net ionic equation by getting rid of the spectator ions, the ions that were there on both sides. And because they're there on both sides, we know they weren't really doing anything in the reaction. Those 6 nitrates were there at the beginning of the reaction. They were still there at the end. They didn't do anything. They weren't important. Those 6 ammonium ions were there at the beginning of the reaction. They were still left over at the end of the reaction. They didn't do anything either. So by canceling those out, we can rewrite the reaction with just the important parts left over, the parts that were actually doing reacting. So what was the reaction that we accomplished here? In the net ionic equation, we can see we put together 2 gallium 3+ ions with 3 carbonate ions to make a precipitate of gallium carbonate. That's our net ionic equation.
Are both, I mean, you said that the second one is easier, the net one is easier. So say this question is on the exam, would you care if I put the first one?
I would tell you what to write. I would
Okay.
say balance. So I would say predict the products of this reaction, balance the equation, and write the total and net ionic forms of the equation. So this would make a perfect like 10-point free response question, right? Because there's lots of things for you to do. Give me the correct products of the reaction, which means that you would have to look up and see if they made a precipitate or not, right? So you'd have to figure out if the 2 were soluble, and then write total and net ionic forms of the equation.
Okay.
Are there any other classroom tangents that we want to go on? Mia, I'm not calling your question a tangent, but like we're free-forming it today, right? Any direction we want to go is a good direction. So are there any directions you guys want to go? We can do some more stoichiometry problems together. We haven't done any solution stoichiometry yet today, only stoichiometry with masses.
Ooh, Yeah, that would be really good. Or
Good.
titration, that's very annoying.
Okay, they're not annoying, they're awesome. I really enjoy titrations.
Okay, sorry.
That's all right. Just remember, like, if you call something annoying that is like part of my life's work, that's just a little offensive. Maybe just a
Oh,
little.
oh no, Dr. Musk, come on now. I mean, I'm still learning.
I
It's
know.
learning pains.
Learn. Okay. So maybe we use the term uncomfortable.
I respect that. Okay.
And there are a lot of really good solution stoichiometry problems in the back of chapter exercises, if I remember right. Of course, I've looked at 4 different books for exercises in the last couple of days. So I think that the best one of them actually was this one, which is great because it's also free. There's so many good ones here. I like number 57. Let's do number 57. So it looks like we're using our balanced chemical equation to relate a number of moles of a reactant to a number of moles of another reactant again this time, huh? So does somebody want to talk through the big principle that allows us to solve this problem? What does that chemical equation tell us that allows us to solve this problem?
We have our moles. We have our moles we have moles and we have volume, I guess.
Is it
Right.
moles and volume? What's that capital M tell us? What is that a unit of?
Moles per liter.
Good, concentration, right? So that's moles per liter. Anytime we know both a number of moles per liter and how many liters of that solution we have, then we can use those to solve for a number of moles of something, right? So what do we know the most about? What can we solve for a number of moles of here? What do we have both a molarity and a volume of? Which reactant?
CuNO3, and yeah, we've got the 43.88 milliliters and then the molarity of it.
Yep. So we can figure out how many moles of copper 2 nitrate we have, right? It has to be copper 2 nitrate because copper can be +1 or +2. And if we know how many moles of copper 2 nitrate we have, we can calculate how many moles of potassium iodide we can react with, right? So that's our pathway for this problem, is solve for a number of moles of copper 2 nitrate, use the coefficients from the balanced chemical equation to figure out how many moles of potassium iodide we're going to react with. And then we can go from moles of potassium iodide to volume of potassium iodide solution using that concentration as a conversion factor. All right, let's give it a shot. So 43.88 milliliters of solution. I'm going to go ahead and do the conversion to liters in my head. So I have 0.04388 liters of my copper 2 nitrate solution. Remember, we can use the concentration of that solution as a conversion factor to convert from liters into moles. So this particular solution of copper 2 nitrate has 0.3842 moles of CuNO3 per every 1 liter of solution. That's what that concentration tells us. Now, from our balanced chemical equation, we can see that for every 2 moles of copper 2 nitrate that we put into the reaction, we react with how many moles of potassium iodide?
Four.
Oh,
Very good. Right from the coefficients in the balanced chemical equation, right? So why am I converting to moles of potassium iodide? Because it's asking us what volume of the potassium iodide solution we need to use. So right now, if I solved, I would be left with how many moles of potassium iodide I needed to use in the reaction. But it's asking us what volume of the Ki solution instead. So we've got to convert this moles of potassium iodide into a volume of a solution. We can do that using the concentration of that solution. So this is the concentration in moles per liter of potassium iodide, which means that every 1 liter of the solution has 0.2089 moles of Ki in it. Now, this is a weird way to use that concentration, but concentration is a conversion factor. We can use it to convert from an amount of stuff into a volume, or we can use it to convert from a volume into an amount of stuff. We've done it both ways in this problem. And then finally, since the initial volume of the one solution was in milliliters, let's go ahead and convert these liters of solution into milliliters instead, even though the problem didn't ask us about it. All right. If I gave you this problem and you told me how many liters of the potassium iodide solution, 10 points all day. All right. But I'm thinking that it's probably going to be a number of milliliters that's a little bit nicer and tidier an answer. So to 4 significant figures, I'm calculating 161.4 milliliters of Ki solution. Anybody else get the same thing?
I've got the same thing, but I did a different equation.
I also took a different route, and now I'm not sure
Okay,
which is.
so tell me what you guys did different.
Let me go first.
I don't
think
care
I-
who goes first. I'm
I
stopping my screen share. Does somebody else want to share their screen and show me what they did? Or do you want to talk me through it and I can write it down?
so I think I ended in the wrong units actually. I messed up my third conversion actually. Never mind.
Right here, sorry, right here that you can't see because I stopped sharing my screen. So your third conversion, you mean this one right here?
I'm kind of confused on, can you like describe again? Oh, sorry, Mia, your mic is off.
It's not, I'm just not talking.
I flipped it. That's what I did, and I ended up in the wrong units.
Yep. So because you want to cancel your moles of potassium iodide out, we have to use our concentration flipped upside down here. That's the only way to get those moles of potassium iodide to cancel and leave us with a volume of solution instead. All right. So when you go back and study this problem later, think about what we're doing in each case. Here, that first conversion, we're using concentration as a conversion factor to convert from a volume of solution into a number of moles. Here, we're using our conversion factor to convert from a number of moles into a volume of solution. That's why we use the reciprocal of the concentration here. Rudy, do you want to tell me your alternate method?
Since it was a neutralization, I actually made them equal to each other.
Made
So
what?
I did the volume of potassium iodide times the molarity divided by the coefficient in the equation equals the molarity divided by copper nitrate coefficient.
So you did it with proportions instead of
Yes.
a stepwise conversion?
Yes.
That works perfectly fine. There's actually an alternate way to do stoichiometry. Like all stoichiometry can be reduced to proportions the way that you just did this problem. I have trouble teaching it that way. So
I can hold it up so you guys can see like what I did.
hold on just a second. I'll unscreen share so you can share.
Sense.
Oh my God, Rudy, how did you figure that out?
I noticed there was just like a correlation between You know, the acids, but when they're neutralizing, it can only be done with an exact neutralization. So just made them equal, and you only have one coefficient to solve for, and then yeah. Just made sense to me. I did it with the homework and it worked fine.
It
But
always
only
will.
but only for the neutralization problems.
Well, in the end, you can reduce any stoichiometry to a proportion instead. It is proportions, right? Those coefficients in the balanced chemical equation they're a proportion, right? In this case, it's 4 moles Ki per 2 moles of copper 2 nitrate, right? It's a proportion. If that way makes sense to you, that's perfectly fine. To me, it's a little harder to rationalize how our units all cancel without showing the conversion step by step. So that's why I recommend doing them the way that I do them. But if what you've done makes sense to you and you can track your units carefully with it, obviously you'll get full credit either way. Okay. I sometimes just teach things the way that it's easiest for me to rationalize all the steps. Does that make sense?
And if your equation's messed up, then you're going to have a wrong number.
That's true. Yeah. Without the balanced chemical equation, you're in bad shape.
Can I clarify something?
Sure.
I know I just went over it, but I just want to like say it so I understand. So, so what you did with the 1 liter solution over 0.2089 moles of Ki is just the same thing as you did when you converted in the beginning with the 0.3842 moles over 1 liter is the same. So you can like interchange, so you can go from liters to moles and then moles to liters, but just
absolutely. Like, so Sarah, think of it this way. All right. Using molar mass, we can always convert from grams to moles, or we can convert from moles to grams, just depending on which way we put that conversion factor, right? Okay, anytime we're using a concentration as a conversion factor, we can use it to convert from volume of solution into amount of stuff, in this case, moles of stuff, right? Or we can use it to convert from moles of stuff into volume of solution. We just have to have the concentration flipped upside down to make the units cancel to do that.
Perfect.
Isn't that cool?
Yeah.
It is really cool. Yeah, that's one of the things that I love about stoichiometry is that the same principles that we used all the way back in chapter 1, where a conversion factor could be used either way, like upside down or right side up, we can convert from milligrams to grams or from grams to milligrams using the same conversion factor, right? This is the same thing, just a different kind of conversion factor. Awesome. There any more types of problems you guys want to do an example of? We do have one more session on Wednesday as well. And our time is getting short for the grace period for homework assignments. So if you guys still have outstanding stuff, make sure you get that stuff finished up as soon as you can. Nothing? All right, we're at 1 hour and 20 minutes. That's a pretty normal amount of time to spend together for recitation. So I hope you guys found this interesting. And I had fun. I hope you had fun too.
It was nice. It was very
good.
nice.
It was very helpful.
I'm glad. Okay,
So
I'll see you guys on
time.
Wednesday. Remember, I've still got office hours tomorrow and Wednesday as well. All right. So if you need individual help with a problem, then make sure you stop by and we can spend as much time as you want within that hour anyway. An hour is a pretty long time to do a couple problems. Okay. Have a good night, everybody.
Bye.
Bye, guys.